Okay, so we're on lesson 8.2, the first lesson in here. So 8.2a. So this is the formula for the one sample z interval. We also often call this one prop interval for proportions or something like that. One prop meaning one proportion. When the conditions are met, a C percent, like a 95% confidence interval for the one proportion is, so p hat, that's the point estimator. We get that usually from the problem, just, something divided by something, plus the critical value. We're going to learn more about how to calculate that today. And then times, you might have learned that formula there on the right. That's for standard deviation, so a proportion. So square root of PQ over N. Okay. So in order to apply this formula, you really have to check count them three conditions. So the first one we haven't seen yet. The other two we've actually seen numerous times. So the first one is it has to be random. For that point estimator, you have to have a random sample. So that's just kind of a given. It's stats. We don't like to just choose people. We choose people randomly. It's called a random sample, right? So in order for that point estimate to be valid, you need to have a random sample here. In order for the z critical value to be valid, you must meet the, I believe it's the less than 10%, large counts condition. Large counts is z critical value. So you do the NP greater than or equal to 10, NQ greater than or equal to 10, you check that condition, and then less than 10% is for standard deviation. I remember that, yeah. So make sure that you're sampling less than 10%, and so we can call it independent enough for it to work there. So those are the three conditions you have to check for confidence intervals when you're dealing with one prop or one sample proportions. Technically, this is kind of and you'll see this formula. It is actually called standard error, but when we're talking about the standard deviation of the statistic here, so we will call it standard error. We should call it standard error. We might slip and call it standard deviation, but it's technically standard error. This is the overall big formula. So point estimate is plus or minus the margin of error. But to get the margin of error, you really need two things multiplied: the critical value times the standard error, technically, of the statistic. So if you multiply those two things, you get that margin of error. So the margin of error is dependent on the critical value. Critical value is dependent on what percentage your confidence is, and so forth. So these are the three conditions you check. Is it come from a random sample? Is it large, less than 10% of the population you're sampling, and then large counts, at least 10 successes and fails. Okay, I think this one we just have to check the conditions here is what it's asking. So Mr. Buckley's class wants to construct a confidence interval for P, the true proportion of red beads in the container, which contains 3,000 beads. Recall that the class's sample of 251 beads had 107 red beads and 144 other beads. Check the conditions for constructing a confidence interval for P are met. Okay, so what are the conditions we need to check? Did it come from a random sample? Because then we could do our point estimates. So random sample, recall that the class's sample of 251 beads had 107. So it says the class's sample, I think we're assuming it's a random sample. Kind of make that assumption. It'd be nice if it said it, but it didn't. What is the large counts condition we have to check? So large counts means NP and NQ. So if you get your calculator out, let's see, what is our P hat here? So had 107. So 107 divided by, we took a total of 251 in our sample. So we get 0.426 is our P hat. So we do NP, so we sampled 251. So 251 times P is that. And then 251 times, parentheses, 1 minus that, or the Q essentially. Those are both definitely at least 10. So NP is at least 10 and Q is at least 10. We sampled 251 out of 3,000. That is less than 10%. 10% is 300, so we're good there. So we checked all the conditions. And that's what we did. Okay, how do we get the z critical value? This is kind of important. So I would highly recommend drawing this. So let me get to the problem first. So we wanted 95%. So what I do is I get a pencil and paper and draw it. This is a very common one, so you might actually end up really memorizing this. But you draw this, so you go, okay, I want 95% confidence. So you really want that. Whoops, 95%. So this point, wherever that is the z critical value. Technically, this point right here is the negative z critical value. Now, honestly, because this is 95%, it's going to be very close to the empirical model, which is, it's going to be very close to 2 standard deviations. I don't think it's exactly that because that's more, empirical model is more of an estimate tool that we use. It's not actually exact. So we could use our calculator to get exact answers. So the command you use is not norm CDF. We know the percentage that we want. This is all the shaded area here between those. So we know the percentage is 95%. But actually, to find this value right here, we know there's 2.5% over here and 2.5% over here. So if that's true, I really want, what's for inverse norm command to work, you can go inverse norm. It asks for the percentage, and you're going to put 0.975, right? Because that's where this point is at. 97.5% of the data is to the left, only 2.5% is right, because we split that 5% equally on each side there. So you're going to get out your inverse norm command. So on your calculator, I think it's menu 6.5 instead of 2, it's going to be 3. And area is 0.975. Standard deviation 0 and 1, I think. So we get 1.96. So the z critical value is equal to 1.96. Now some students do this. They just take that one on the left and they say, well, there's only 2.5% to the left there. So they say menu 653. They say 0.025. And you should get the negative version of the z critical value. You do. So that's one way of doing it is they find that and then they make it positive. The z critical value is always positive, so it's never actually going to be negative. That's what they did there. They drew a picture of that. By the way, I just mentioned some students use a table, not in my class, but some students use a table. It's not as accurate. It's harder to do. It's easier with technology. Just use inverse norm. Type it in either 0.975 or 0.025, and you'll find the z critical value, 1.96. And weirdly, you might actually memorize that one. We use that one so much. It's so close to 2 that I just kind of know, oh, 1.96. I don't have to calculate this every time because, again, 95% confidence is pretty common as far as things go. According to the 2016 Pew Research report, 73%. So 73% of American adults have read a book in the previous 12 months. I'm imagining St. Mary's girls are even higher than that. This estimate was based on a random sample of over 1,500 American adults. Assume the conditions for inference are met. So in this case, we don't have to check the conditions. They said, hey, those guys are met. So we don't have to check, is it random sample, less than 10%, large counts, and p is greater than or equal to 10. Okay, so determine the z critical value for 90% confidence interval. So I'll get out a sheet of paper. I'll draw 90% right here. If there's 90% in the middle, then on the sides, there's going to be 5% and 5%. It splits up. It has to add up to 100%. So if you want that right there, how much is to the left of that? Go to your inverse norm command, menu 653. 0.95 is to the left of the z critical value, and so the answer should be z critical value is equal to 1.64, looks like. And that's actually a very popular one as well, so we can do that. Construct a 90% confidence interval for the proportions of American adults who have read a book in the previous 12 months. Okay, so let's get the p hat here. So it looks like, oh, well, it's 0.73. Right, so if we start constructing this, right, so let's kind of, so p hat would be 0.73, that's our point estimator. We already checked the conditions, or at least it was assumed. Z critical value is 1.64, and the standard error, technically it's called, is p hat q hat, so 0.73 times That's at 0.73 times 0.27, the Q there, or the 1 minus P, all over N, which was random sample of 1,520. So 1,520. So 1,520. So it's not a bad idea when you're first starting this to do each part individually. Can I go a step at a time? I think I'm going to do that now. As we get better at this, there's ways to kind of make this quicker. There's a way to do the whole thing in calculator, actually, which we'll get to. We will show you that definitely very soon. So I'm going to do square root, control divide to get the fraction, and that'd be 0.73 times 0.27 all over 1520. So standard deviation is that, so 1.64 times 0.011. Oftentimes I'll round that one to maybe 3 or 4 digits, and then I'll use the exact number in my calculator. So over here, I really want to multiply those right two numbers. So I'm just going to put times 1.64, and I'm going to grab the actual number there. So I'm actually, these are very accurate. I'm taking that 0.011387 times the 1.644. I'm taking the actual numbers there. So mine's going to be more accurate than a rounded one. I prefer to do it that way. On my paper, I'm showing the rounded number of 0.018, 019, I should say, if I round it. But oftentimes, again, I'll just kind of go, okay, so that is plus 0.73. Whoops, I was typing, not on the calculator. So plus 0.73. So the bigger number is going to be 0.7487. I probably went too many there, but get the idea. The smaller number would be 0.73 minus, again, I'm trying to grab those actual numbers there, the 0.019. And so 0.7111. 3 or 4 decimal places is probably fine there. 1112, I guess. So there is my interval. So interpret the interval. So I am 90% confident that the interval from 71.1% to 74.8% or 9% contains the true proportion of American adults who have read a book in the last 12 months. So that's how we roll with that, and let's see what they did, if they did anything different. So they got the 1.645, they got that same interval, I believe, pretty close. They might have rounded slightly differently. Ours is probably more accurate. Have read a book in the last 12 months. That's exactly right. Okay. So 4-step process. So we technically should state the parameter, CF, so that you want to estimate and the confidence level. So we're trying to figure out what the true proportion of something is, right? That's the P value. It often identifies the the confidence level, so 90% or 95%, whatever it is. Those are the two most common. Identify the appropriate inference method. So one prop, Z interval, or something like that would be fine. Check the conditions. You want to check all 3 conditions. If the conditions are met, then you do the calculations, and then you interpret your results. Okay, I think we already had that. Oops, I'm going the wrong way. Okay, there we go. A recent poll of 738 selected cell phone users found that 170 of the respondents admitted to walking into something or someone while talking on a cell phone. Construct and interpret a 95% confidence interval for the proportion of all cell phone users who admit to walking into something or someone while talking on their cell phone. That actually happens, I believe. So you would start with state, what is this? So this is a 1 prop Z interval measuring the proportion of cell phone users who admit to walking into something or someone at a 95% confidence level. We need to check the conditions, right? So what are the conditions? Is this from a random sample? selected cell phone users. So I guess we would assume it's from a recent poll was a random sample, but it didn't state it. It'd be nice if it stated it. Then you do your conditions, right? So you want to do like NP, so 170. So 170 divided by 738. So P hat is 0.23. So that times N times 738 would be, that's the number of successes. I'm just going to copy that. Instead of that P hat there, it's going to be parentheses 1 minus that. So 568 failures. So there's at least 10 of both, which is good. 170 is, well, let's see, 170 divided by 738. Wait, oh, I'm sorry. 738 is less than 10% of, let's see, what are we doing? Less than 10% of all cell phone users who admit to, so there's tons more. So that's definitely less than 10%, so we're good there. We checked all the conditions. You would then start, setting up your proportions and things here. So you'd say you start with P hat, right? So P hat is 0.23. I'm just going to put 0.23. Again, sometimes I use the more accurate number there. Times Z critical value. You could just know this. This is for 95% confidence. So I know it's 1.96. If you don't know that, you could draw the curve. There's 95 within there, which means there's 2.5% here. So you do inverse norm 0.975, and it gives you the 1.96 times square root of PQ, so 0.23, times, in the numerator, that's 0.23, times 0.77, all over n, which is 738. It's all underneath the radical there. Okay, so then you start, get your calculator out. So let's do that first part. So square root, whoops. So square root, control divide. So 0.23 times, I guess I'm not using the exact number there. I'm okay with that, 0.77. We're pretty, as long as you show your work, we're okay with a little bit of rounding. 738, so we get that number. I'm just going to do the next step in my calculator. So times 1.96 is that. We're going to add that to 0.023. 0.023 minus that number. So that should be our interval. So I did a lot of work there. So this one is 0.015 times 1.96. Those two multiplied together is 0.003. And then we added and subtracted, and we got a lower bound of 0.01 or 02, I guess I'm going to say. Whoops. 0.02. And an upper bound of 0.026. Let's see if we got 0.02 to 0.026. Check the conditions. 0.2 to 0.206. I think that's what I got. Oh, wait, I had 0.02. Because it's 0.23. Where did I have that? I said 0.023. Oh no, right there. So it all goes to naught if you grab the wrong number. So I said 0.023 and I should have said 0.23. There's a plus 0.23. Wow, it's easy to make a mistake like that. And then 0.23 minus that number. I think that was it. 0.23. I'm confusing my numbers. So 0.23, the margin of error was 1.96 times that. So that is going to be minus that, so plus 0.23. That's my lower, whoops. That's my lower bound. I think I used the wrong number for that one. Yeah. Boy, messed it up. So that part times 1.96. Get that number correct. So that's our margin of error. It's hard to do this all in the calculator. I probably should have showed a step at a time. This is actually good for you guys to see because it's very easy to actually, if you do it all in the calculator, to make a little bit of a mistake there. So this is the part that I think I messed up on. So if I'd written that, I would have seen it a little easier there. So this is 0.03. So then I'm going to do both those things to get my lower bound and upper bound. So I'm going to, on my calculator, do the 0.23 minus that number and the 0.23 plus that number, the margin of error. Now I got it right. So 0.199, which is 0.2, and 0.26. Now we got it right. There's actually a cool thing is that we can check our work in this. We can actually do this on the calculator. So I'm going to go ahead and show you this now. It's really powerful. So I would have checked my work and said, well, no, did I get it right or not? And I'd either catch your mistake, or if you can't show your work correctly, you can always just trust the calculator this one and go with what the calculator says. You can actually do the interval in the calculator. You want to show your steps. We want to see those steps for full credit, but you would get pretty substantial partial credit, sometimes full credit for just knowing the actual interval and interpreting it. That might be what they're asking for. They may not care about the individual steps on certain problems. So it kind of depends on the problem. So if you go to menu, statistics, look at that, confidence intervals. There's what's called a 1 prop Z interval. I think that's what we're looking for. Let's see. So it's been a while. It's either Z interval or that. I'm going to try 1 prop Z interval. So number of successes is 170 out of 738. And confidence level is 0.95. It defaults to that, which is kind of nice. It says the lower bound is 0.19. Oh my goodness, that's exactly what I had in my calculator. And then 0.26073. So they actually do the lower. Do you see the lower and upper bound there? They actually tell you the p-hat, the margin of error. So even just looking at your calculator there, let's say I didn't do this by hand. I could show this work. I could say p-hat is 0.23 plus or minus. The margin of error is 0.03. 0.03 there. I'm getting this from the calculator. And then the lower bound is 0.199, so I'm just going to say 0.2 because it rounds, comma to 0.26. And then I could interpret that value, right? So you can get all that just from the calculator. So you can definitely double check yourself because again, especially if you're trying to do all the calculator or you're just doing a lot of steps, it's easy to make a mistake, right? So it's really nice that you get, in fact, sometimes I'll honestly do the calculator part first. So sometimes I'll just do the interval on the calculator first, and that might be the way to go here. Again, don't forget to interpret. They probably will ask this question, construct and interpret. We are 95% confident the interval from 0.2 to 0.26 captures P, the true proportion of all cell phone users who admit to walking into something less than under talking on the cell phone. You're expected to do the entire 4-step process that includes clearly defining the parameter, identifying the procedure, and checking the conditions. The margin of error does account for the sampling variability. Okay, so done with the lesson. Just try a few examples. Katy Perry is currently the most popular account on Twitter. It's about 100 million followers. Mr. Starnes wonders what proportion of Katy Perry's Twitter followers are female. So he selected a random sample of 500 of Katy's followers. In the sample, 308 are female. Check if the conditions for constructing this confidence interval for P are met. So what are the three conditions? So is this a random sample? It does say random sample. I love it. Okay, so that's great. Is that less than 10%? So 500 is less than, she has more than 5,000 followers. Yes, that's less than 10%. And then you would check the NP and Q. So this would be 308 divided by 500. Is that your P hat there? So that times N would be times 500. And then 1 minus that P hat times 500. You have at least 10 successes, at least 10 failures, so it passes that condition as well. So you got it. Just how do you get the Z critical value there? So again, you're going to, in your calculator, do the inverse norm. So menu 653, inverse norm, 90%, so there's 5% on each side, so 0.95 is to the left of the Z critical value, and that should give it to you 1.64. You might even recognize that number, it's very popular. Construct a 90% confidence interval. Assume all conditions are met, so you would then do this. Let me just refresh how to do this in the calculator. So menu statistics, confidence intervals, one prop, Z interval. And so the number of successes, there were 308 followers out of 500. Confidence level is only 0.9, so we're going to put 90 or 0.9. So now we know, if we were showing work and we didn't show all the individual work, it'd be nice to show the individual work, but P hat would be 0.616 plus or minus the margin of error, which is 0.035 or 0.036. The Z critical value, you can almost work backwards here. Right? We know the lower bound is 0.58, the upper bound is 0.65. Working backwards, the critical value we just got it a second ago was 1.64. Square root of P hat Q hat, so it'd be 0.616 times 0.384. You can use your calculator if you need to for that, 1 minus that, and then over N, which is, I think it was 500. And that would be like perfect work showed. You notice I got most of that from my calculator. I kind of worked backwards. So it's kind of a neat way to do it. Do the calculator first, get your answer correct, get your second to last answer correct, and then work backwards and show that. So I think that's actually a good way to go. Now you do have to show the conditions if it asks for it. It did not ask for the conditions here. You should state though what it is, right? So this is a 90% confidence interval. It's a one prop Z interval for the proportion of folks who are female from Katy Perry's followers. So that's the formula of constructing it. Interpret that. We are 90% confident the interval from 0.58 to 0.652 captures the true proportion of Katy Perry's Twitter followers who are female. So, more than half of them are female. So that makes sense, I think. And so I think that's enough for today. Let's call that a screencast.